Hello everyone, welcome to my talk. My name is Fenggang. I'm from University of Minnesota. This is a joint work with Ming-Hong, Baoquan, and Professor David Du. And this paper is about adaptive caching for LSM-based key-value stores. Let's start from key-value stores. Key-value stores are very popular. They are used in web searching, social networks, e-commerce. And there are many types of key-value stores. Among them, the LSM-tree-based key-value stores are widely used. Here are some examples. Google has LiveDB, Facebook has RocksDB, and eBay is using Cassandra. So let's zoom into what's the internal operations in an LSM-based key-value store. In a typical setting, there are DRAMs and storage. And in the write operation, the user will store a key and value pair into the key-value store. First, the key and value pair will be inserted into a memory component, which is a sorted data structure. It can be implemented as a tree or skip list. And the in-memory component has a size limit. Once the limit is reached to the maximum predefined value, all the inserted key and value pairs will be read in a batch into the storage as a level 1 storage component. And the storage component also has its size limit. Once the level 1 component has reached to its size limit, it will be merged into the next level, which is level 2. And level 2 will be 10 times larger. So we can imagine the time goes on, the multiple level 1 merge to level 2, and the level 2 has reached to its size limit. It will be further merged into the next level, and so on and so forth. In this talk example, there are 3 levels, but in real production setting, there can be more levels. We can see here that in this LSM-tree-based key-value store, the key and values are batched and read sequentially from time to time, which is good for the storage write because it never performs scatter in place update. So this multiple component is good for write. And on the other hand, this multiple component structure or design is not so good for read performance. So here we can see why. There are 2 distinct types of read operations in LSM-based key-value store. One is point lookup, meaning using one key to retrieve the value. The other is range query, meaning using a key range, and the key-value store will return all the key and values which falls into this key range. So let's see the point lookup. The user has one key to query, and because this multiple component design, each component is covering the whole key range. So the key may be possible in any of the component. And because data flow is from top down, and we will check from the uppermost component to see whether the value is there. And because it will be stored the most updated version of the value. And we query the in-memory component. If it is there, the value will be returned to the user without further searching into the storage. And if it's not in the memory component, we will query the first level to see whether the value is there or not. And if the key is not found, we will further search the second level and all the way to the bottom. And please note here, the I/O unit is one block. It's not a single key and value. And the block is have a typical size of 16 KB. And the one block is a sorted range of key and value pairs. So we can see the LSM-based key-value store suffer from read performance issue. it potentially should check every level to query one particular key. And it has to fetch the whole block when only one key is queried. This is point lookup. And similar for range query, the user specify a key range, and potentially every component will have overlapping key range of the range of interest. So data block from every level should be fetched into the memory. Then a merge will be performed to construct the final result that can be returned to the user. So both the point lookup and range query will fetch many blocks only for one query, which causes the read performance issue. And how to solve this read performance issue? In order to save the storage I/O, one typical thinking is that if some item is frequently accessed, can we use cache so that next time this item is accessed, we can directly return it from a memory instead of fetching them from the storage so that the storage read will be saved? The answer is yes. This is because the key-value workload has a hotspot. There will be many reports reporting this hotspot phenomenon in this key-value workload. For example, in mem cache, one key can contribute 20% of the server's request. And for JBDB in Facebook, 1% of the keys can take half of the total point lookup. And range query can also have hot ranges. So this is good news. So we can use cache to retain the frequently accessed items in the memory to save the storage read. But the problem is not that easy. This is because popular caching schemes does not fit in our LSM-based Key-Value Store. This is because there are many unique challenges exist in our LSM-based KVS. For example, the data has different size and the level. One key-value pair can be much larger than the other key-value pair. It may result in different level of the hierarchy. So the cache cost and benefit is different. Also, there are distinct type of reads, meaning there are point lookup and range query, which have very different requirements on the caching items. And look around the existing solutions. If there are general caching schemes, they have no special analysis about the different caching costs and caching benefit in LSM-based KVS. But there are many LSM-based KVS already be there for quite a long time. How well do they do? And what are their caching schemes? It turns out existing solutions will favor only one particular workload. And if it's another workload or a changing workload, it will be not as efficient. So here are more details. We have a little bit investigation about what can be cached in the caching space. So we can cache block. Caching block is natural because block is the I/O unit. So once we have fetched a block from storage, we can just leave it there. And this is good for range query because one block has a sorted list of all the key and values falls into this particular range. And after merging with other blocks from other levels, we can have the result. But caching a block is not efficient for point lookup because only one or two hotkeys will keep one whole block in the memory, and there will be some irrelevant keys which do not get access. This is also in this block. And such key and values is a waste of caching space. Those space can be otherwise used by cache other key and values to improve the point lookup performance. So we have another option that to cache individual key and values. Then we can have one step further, because some of the value can be very big. And one of the optimization is we can just cache a pointer of the value. A pointer is nothing but a location into the storage. So if later this key got to be queried, we can find the pointer in our cache, and we perform one extra I/O to get the value. So by doing this, we can cache multiple key and pointers. This has the potential to have even better performance than caching only one key and its big value. And as a summary, we can see that each of the cached item can have its favorable workload. For example, the block cache is good for range query, but it's not efficient for point lookup. And for key value cache, is key value and key pointer cache. It's good for point lookup, but it cannot support range query. Because looking into individual cache key and values, we can't figure out what is the next larger key. We still have to check the storage. The key V cache and the KB cache, we collectively call them point cache because they only support point lookups. Here is we did a little survey about the state-of-the-art industrial solutions about the caching component. So it turns out to be none of them support all three types of caching components. For example, LSM-DB only support block cache, which means it can support the range query, but does not have a efficient support of a point lookup. And on the other hand, Cassandra supports both the KV cache and KB cache, but only KV and KB cache cannot support range query. And another issue about the existing solution is that even if like RocksDB and Cassandra has like 2 out of 3 components already be there, but the size of each component is fixed and it is predefined. So it may be good for one type of workload, but it will not be efficient to a different workload or a changing workload. So this motivates us to design AC key, which has all 3 different types of components. So it will support both the point lookup and range query. And also, we want the size of different caching components be adaptive. This allows us to change the size of each component if the workload has been changed. Given the high-level idea, the next challenge is how do we link the size and the workload? For example, how do we adjust the size of each different cache component according to the dynamic workloads? We answer this challenge by ghost cache. So here in this figure, we show the cache is divided into the point cache and the block cache. The point cache, as we have mentioned before, is comprised of both the key value cache and the key pointer cache. We will explain more detail in later slides. Now, in the high level, we have boundary between the block cache and the point cache. How do we adjust the boundary between those? The answer is using ghost cache. Ghost cache is also a cache, but it do not store the real entry. It only stores the metadata evaded from the real cache. For example, if one block is evicted from block cache, only the block number will enter the ghost cache. This is to keep a record of the recent evicted items, so that if later there's an access to this particular block, we know that we have made a wrong decision to evict this block. Because if this block were in the cache, it will be a hit by this time. So in this case, we want the block to be larger so that this block will not be evicted. In this time, it will be a hit for this block. The operation will be Each time there is a block ghost cache hit, the boundary will be moved toward the left, shrinking the pointer cache, enlarging the block cache, so that the block cache will be larger to incorporate more blocks and to reduce the evasion. And the same story for the other part of the boundary. If there is a ghost hit in the ghost point cache, and the boundary will be moved toward the right. So as the workload goes on, the boundary adjustment will be constantly performed, and eventually it will reach to a dynamic equilibrium for a given workload. And if there's a phase change in the workload, the boundary will be adjusted accordingly. This is a higher level of how we adjust the boundary between point cache and block cache. And within the point cache, we will have a same technique. So here we have like more detailed figure. In the upper level, we will adjust the boundary between point cache and block cache using ghost cache. And also we apply the same logic in the lower level, which comprise both the key-value cache and the KB cache. We use the ghost cache to adjust the boundary to. So this is a hierarchical adaptive caching scheme. By using this scheme, we can adapt the size of all of three components, the block cache, key-value cache, and KB cache, according to different type of workloads. In order to make this hierarchical adaptive scheme work, there are also other challenges. We solve them here. For example, how do we measure the caching efficiency factor to consider different caching entry, different cost and benefit of different caching entries? So we can make a correct decision in evaluating specific item or in the boundary adjustment. And also there are special operations specific to the LSM-based KVS. For example, the compilation operation and the flush operation. And we have special handling logic. The design details is in the paper too. Evaluation. So we implement the AC key based on RocksDB, and RocksDB is widely used in the industry, and it's open sourced. We implement AC key and evaluate against like other competing schemes with various workloads and system settings. For a complete evaluation result, feel free to check out our paper. And we will only present two representative evaluation results in this presentation to illustrate how our adaptive scheme goes. Here we have like 4 other competing schemes. The RocksDB is an industry solution. We use the out-of-shelf RocksDB, and by default, it is the pure block cache configuration. So we just use it as is. Besides this, we also have the pure key-value cache baseline and pure KP cache baseline. And also we have this offline scheme, which will try out different combinations of block, KV, and KP with 1/10 of the granularity and pick the winner. So the y-axis is the QPS, the higher the better. And we can see the result here. We vary the range query ratio. In the left-hand side, the range query ratio is 0. This means it's all point lookup workload. And in the right-hand side, it means all range query workload. As we can see that our scheme outperforms all the other schemes. One thing to mention is that because the offline scheme only explores the combination in 1/10 granularity, it may miss some optimal points. But our AC key is adaptive. It can explore the whole solution space. So that's why it can have like even better performance than this one-tenth granularity scheme. To show direct evidence about how the adaptive goes, we have the next test, where we construct a phase-changing workload. In the first phase of the workload, we have this pure range require workload, and later we change it to a pure point lookup workload. And we have two figures. The top figure is shown the real-time size of the 3 different caching components. And the bottom shows the performance in terms of QPS. And like by comparison, for comparison purpose, we also have this offline scheme, the performance, real-time performance plotted in here. In the first 1 million queries, we use pure range query. So as we can see from the top figure that the AC key has distributed all the caching space to block cache. This is because the point cache, meaning KP cache and KV cache, cannot support range query. So AC key correctly distribute all the caching space to block cache to support range query. And after the 1 millionth operation, the workload is changed from pure range query to pure point lookup. And we can also see from top figure that the AC key has correctly shrink the block cache all the way down to 0. This is because the block cache is cannot efficiently support point lookup, and KV cache and KP cache is better off to support point lookup. And also, after the KV and the KP cache has reached to the balance, we can see the performance of our AC key outperform the offline scheme again. And this is because the offline scheme is a fixed scheme, even if it can beat all the other fixed schemes. But it may not be the best configuration in each individual phase. So that's why our adaptive scheme can have one good configuration in the first phase to beat this offline scheme, and change to another very different configuration and beat the offline fixed configuration again. And with this, we have introduced these 2 tests showing our advantage of our adaptive caching scheme. So summary. LSM-based Key-Value Store is widely used, and the multiple component design make it right optimized, but it has many like a read performance issue also because of this multiple component design. In order to solve this read performance issue, we use AC key, which is an adaptive caching scheme for this LSM-based Key-Value Store, using the caching angle from a caching angle. In AC key, we integrate all the key value, key pointer, and block cache components. And we also design a hierarchical size adaptive scheme to adapt the size of different caching components that can be adjusted according to different workloads. And the evaluation shows it can outperform industry solutions. So with that, I conclude all the contents of this presentation. Thank you very much for the attention.